Good morning to all. Today we will be discussing the 8th chapter, that is D and F block elements. So as we all know, the modern periodic table is comprised of 4 blocks. They are S, P, D and F. In this particular periodic table, the 4 blocks are differentiated using the color codes. The blue colored block is the S block elements. The green colored block is the P block elements. The center lying block in between S and P, which is given the red color, is the D block elements. And the block at the bottom of the periodic table, which is in yellow color, is the F block elements. So what is the criteria behind classifying the elements into different blocks? The concept is very simple. It is simply based on the criteria that the last electron enters into which orbital. For example, sodium, the atomic number is 11. So the configuration is 1s2, 2s2, 2p6 and 3s1. The last electron enters the s orbital and thereby sodium is regarded as an s block element. In the case of oxygen, the atomic number of oxygen is 8. So thereby the electronic configuration is 1s2, 2s2 and 2p4. That means the last electron enters the p orbital. Then that is why oxygen is regarded as an p block element. Similar is the case of D and F block elements. In this chapter we will be discussing the D and F blocks in detail. So the first point, D block elements. The elements lying in the middle of the periodic table belonging to group 3 to group 12 are called D block elements. The general electronic configuration is n-1 D 1 to 10, n is 1 to 2. So in this particular periodic table you can see that the groups which is marked in red color, that is from group 3 to group 12, they are called D block elements. They are also called transition elements. What is the reason behind that? So we already know that the S block element, they are completely comprised of metals and P block elements of non-metals. So the center lying D block actually acts as a transition from metal to non-metal. So that is the reason behind the D block elements are also called transition elements. Next, regarding their electronic configuration, the general electronic configuration of transition metals is n-1 D 1 to 10, n is 1 to 2. So focusing on electronic configuration, we will discuss the electronic configuration of scandium to zinc. So here you can see that the outer electronic configuration of scandium is argon 3d1 4s2. As per the Aufbau principle, the electrons are entering according to increasing energy levels. So only after 4s orbitals are filled, only then the 3d orbitals are filled. So in case of scandium, even after filling the 4s orbital, one electron is left and that electron enters the 3d orbital, and thereby the electronic configuration is 3d1 4s2. So in scandium, the last electron enters the d orbital, and that is why scandium is regarded as a d block element. Next, in the case of titanium, the outer electronic configuration is argon 3d2 4s2. That means after filling the 4s orbital, 2 more electrons are left, and those 2 electrons enters the next d orbital, that is 3d. So the electronic configuration is argon 3d2 4s2. So in all these elements, you can see the last electron enters the d orbital, and thereby these elements are part of D block. Okay. The second definition, transition element. A transition element is defined as the one which has got incompletely filled d orbitals in its ground state or in any one of its oxidation state. So that is the definition for a transition element. So the requirement for an element to be part of transition or D block is that it should have incompletely filled d orbitals in its ground state or in any of its oxidation states. So the requirement is incompletely filled d orbitals. Third point, zinc, cadmium, mercury are not regarded as transition metals because they are having completely filled d orbital. So in this particular periodic table, it is clear that zinc, cadmium, mercury, even though they are part of the D block element, which is marked in red color, they are not regarded as D block element. What is the reason behind that? The reason is already dealt. In order for an element to become transition element, the criteria is that it should have incompletely filled d orbital. We know d subshell has got 5 orbitals, and each orbital can accommodate a maximum of 2, and thereby 5 into 2 will get d subshell can accommodate maximum 10 electrons. So D10 means the D subshell is completely filled. So if D is completely filled, it is D10 and it is not part of D block element. In order for an element to become d block element, the configuration should be d1 to d9. Only if the electronic distribution is between d1 and d9, that particular element can be considered as a d block element. But in the case of zinc, cadmium, mercury, if you write the electronic configuration in the ground state or in any one of its oxidation state, like it will definitely be 3d10. So if it is 3d10, it is completely filled and thereby they are not regarded as transition element. Other elements like nickel, cobalt, etc. If you write the electronic configuration, you can see that the d orbitals are not completely filled. It will be lying in the range of d1 to d9, and thereby the other elements are part of d block or transition elements. So that's a 1 mark question. The question will be like this: zinc is not regarded as a d block element. Why? So the answer will be like this: write the electronic configuration of zinc, and when you write the configuration, it will be clear that the outer electronic configuration will be 3d10, and the requirement for an element to become part of transition element is it should have incompletely filled d orbital. In zinc, the d orbital is completely filled and thereby it is not a transition element. Okay. The fourth point, F block elements. F block elements you can see at the bottom of the periodic table, which is marked in yellow color. So F block element means that the last electron will be entering the F orbital and thereby they are regarded as F block elements. So the elements constituting the F block are those in which the 4f and 5f orbitals are progressively filled. That means in the F block elements, either the 4f or 5f orbitals will be filled last and thereby they are regarded as F block elements. Now we will be discussing about the F block elements, that is lanthanoids and actinoids. So this lanthanoids and actinoids, that is the F block elements, are also called inner transition elements. What is the reason for them being called inner transition elements? From the name itself, it is clear that they are part of transition or D block, but they are present inside the D block or transition element series. So if you closely observe the periodic table, it is clear that the space, the white space given here, 57 to 71, similarly 89 to 103. Those two spaces are vacant there, and that range is filled by lanthanoids and actinoids. Okay. Now we will discuss lanthanoids and actinoids in detail. Lanthanoids, the 14 elements immediately following lanthanum, that is cerium with atomic number 58 and lutetium with atomic number 71 are called lanthanoids. They belong to the first inner transition series. Lanthanum with atomic number 57 has got similar properties, therefore it is studied along with lanthanoids. Similarly, in the case of actinoids, the 14 elements immediately following actinium with atomic numbers 90 to 103, that is thorium to lawrencium, are called actinoids. They belong to the second inner transition series. Actinium with atomic number 89 has also got similar properties, so it is also studied along with actinoids. So that is all about inner transition series. They are also called F block elements and they comprise of lanthanoids and actinoids. Our next topic is the 4 transition series. That means the transition elements of the D block elements are further classified into 4. They are the 3D series, 4D series, 5D series and 6D series. So we'll be studying them in detail. The 3D series comprise of elements from atomic number 21 to 30. To be specific, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Okay. In those elements, the last electron will be entering the 3D orbital. That is why they belong to the 3D series. The next series is from yttrium to cadmium. That is atomic number 39 to 48. In those elements, the last electron will be entering the 4D orbitals. The next series is the 5D series. The 5D series comprises of elements from atomic number 57 to 80. But the point to be noted is that elements with atomic number 58 to 71, those are the elements that are belonging to lanthanoids. So they are inner transition elements. Those elements are not part of the 5D series. In the 5D series, the elements will be lanthanum and then hafnium, and the last element will be mercury, that is with atomic number 80. In the elements of 5D series, the last electron will be entering the 5D orbital. On the other hand, the elements that is in inner transition elements 58 to 71, that is the lanthanoid series, the last electron will be entering the F orbitals. The last series is the 6D series. Those comprise of the elements from atomic number 89 to 112. But the point to be noted is that elements with atomic number 90 to 103, those are not part of the 6D series. Those are the actinoid elements. So the elements belonging to 6D series would be actinium, then rutherfordium, and then it will end in copernicium with atomic number 112. The elements with atomic number 90 to 103 are not part of the 6D series. Next, we have to discuss the physical properties of the D block elements or the transition elements. First, we will discuss the metallic character. All the D block elements are metallic nature. That means they are having strong metallic bond. And the presence of unpaired electron is responsible for this metallic character. For example, the first element with atomic number 21, that is scandium, the electronic configuration is 4s2 3d1. That means there is an unpaired electron in the d orbital. In the case of titanium, the outermost electronic configuration is 4s2 3d2. That means there are two unpaired electrons in the d orbital. And the third element, that is vanadium, the outermost configuration is 4s2 3d3. That means there are three unpaired electrons in the d orbital. And we know the free electrons are like taken into consideration when we deal about the metallic bonds, and most of the transition elements are having free electron, and that is the phenomenon responsible for their metallic character. And due to this, they're having properties like high density, high melting point, high boiling point, etc. Next, we will discuss about the atomic and ionic radius. The normal trend is that atomic and ionic radius decreases as we move from left to right of the periodic table. But in the case of transition elements, there are some anomalies. For example, in the case of the 3D series, the atomic number or the atomic size decreases from scandium to chromium. So as a regular pattern, the atomic size or the ionic radius decreases from scandium to chromium. But the elements like iron, cobalt, nickel, etc. are having almost the same size. There is no steady decrease in the atomic size from iron to nickel. It remains the same. And copper and zinc, they are having a large size compared to the other elements like scandium, iron, etc. So from scandium to zinc, there is an irregularity in the general properties. Normally, atomic size has to decrease as we move from left to right of the periodic table. But in the case of the 3D series, it is like this. From scandium to chromium, there is decrease in the size. As a regular pattern, the size of the atom decreases from scandium to chromium. The size of iron, cobalt, nickel, etc. remain the same. There is no further decrease. It remains the same. And copper and zinc, the size is increasing. So there is an anomaly with respect to the regular pattern. In the beginning, it shows a regular degradation in the size, then it remains the same, and then it is going again. That means the size is increasing. So that is an anomaly. So we have to discuss what is the reason for this anomaly. So to explain this, we have to discuss about shielding effect. In order to explain the concept of shielding, we have to consider an atom. At the center of the atom, we have got the nucleus, and the electrons are arranged in specific shells around the nucleus. The nucleus is always exerting an inward attractive force towards the electrons, and this inward attractive force is responsible for holding the electrons around the nucleus and maintaining the spherical shape. So to explain the concept of shielding, we have to consider two different kinds of electrons. One is the electrons that are present at the outermost shell. They are regarded as the outer electron, which I marked in green color. And next is the inner electrons, that are present in between the nucleus and the outer electron. For our convenience, I have marked them in blue color. So now we have to differentiate the effective nuclear charge exerted on the inner electrons and the outer electrons. So when you compare the net attractive force experienced by these two electrons, it is seen that the inner electrons are experiencing more attractive force from the nucleus, and the outer electrons are experiencing a less attractive force from the nucleus. This is because the inner electrons act as a barrier or a shield, and thereby preventing the net attractive force experienced on the outer electrons. So this kind of decrease in the attractive force from the nucleus is called shielding effect. Reason for that is the inner electron present between the nucleus and the outer electrons act as a barrier or a shield, and thereby preventing the total net force exerted by the nucleus to be felt on the outer electrons, and thereby the outer electrons won't be completely attracted towards the nucleus. The inner electron acts as a shield and thereby prevent the net attractive force exerted by the nucleus. That is why there occurs an irregularity in the atomic size degradation. Normally, from left to right of the periodic table, atomic size reduces because the nucleus charge is increasing with the increase in atomic number. But here we can see in the first 3D series, there is a degradation. The degradation is not proper. From scandium to chromium, it is a degradation size occurs, but nickel, cobalt, etc. are of the same size, and copper and zinc, the size is increasing. So that is an anomaly. The phenomenon responsible for this anomaly is the shielding effect. The shielding effect can be explained with this atomic description. The outer electrons are not experiencing complete attractive force experienced by the nucleus. This is because the inner electron acts as a barrier and thereby preventing the complete attractive force to be experienced on the outer electron. And due to this shielding effect, there occurs an anomaly or difference in the normal pattern of atomic and ionic radius. Our next topic is Lanthanoid contraction. The steady decrease in the atomic and ionic radius of the transition metals, to be specific, the lanthanoids, with the increase in the atomic number is called Lanthanoid contraction. Normally, as we move from left to right of the periodic table, the atomic and ionic size decreases. This is because as we move from left to right, the atomic number increases. With the increase in the atomic number, the nuclear charge also increases. With the increased nuclear charge, the nucleus will be able to experience or exert more inward pull towards the outer electrons. Thereby, there will be more strongly attracted towards the inside, and thus the nuclear size decreases. But in addition to the normal decline in the atomic and ionic radius, the lanthanoids are exerting another steady decline in the atomic and ionic radius. This steady decline in the atomic and ionic radius with the increase in the atomic number is called Lanthanoid contraction. The Lanthanoid contraction can be explained with the help of shielding effect. So in this particular diagram, we can see the cause of lanthanoid contraction. The cause of lanthanoid contraction is generally attributed to the imperfect shielding of 4 electrons. So the phenomenon responsible for lanthanoid contraction is the imperfect shielding exerted by the 4 electrons. So each orbital has got different capability of shielding. Compared to other orbitals, F orbitals are exerting very less shielding effect. So compared to other orbitals, F orbitals are exerting less shielding effect. In this particular atom, you can see the nucleus is in the center and the outermost electrons are the electron present in the 6s orbitals, and the electrons in the 4f orbitals are the inner electrons. So as we already studied, the 4f orbitals will be exerting less shielding effect. So in this particular case, the inward pull experienced by the electrons in the 6s orbitals will be greater, because the 4f orbitals are exerting only less shielding effect. So here the 6s electrons will be experiencing more inward pull from the nucleus, and thus the size decreases. So this steady decline in the size of the atomic and ionic radius with the increase in the atomic number is called lanthanoid contraction, and the cause of lanthanoid contraction is the imperfect shielding exerted by the 4f electrons. Similar in the case of lanthanoid contraction, the contraction is also seen in actinoids, and that contraction is called actinoid contraction. In actinoid contraction, the 5f orbitals, imperfect shielding of the 5f orbitals are responsible for actinoid contraction. Similar to this case, the 5f orbitals will be the inner electrons, and they will be exerting only less shielding effect. Due to this less shielding effect, the nucleus will be able to impart more nuclear inward pull on the outer electrons, and the outer electrons will be pulled towards the nucleus, inside the nucleus, towards the nucleus with more inward pull, and thus there is a steady decline in the atomic and ionic radius. So this is about lanthanoid contraction and actinoid contraction. Our next topic is ionization enthalpy. There is a slight and irregular variation in the ionization energies of the transition metals due to irregular variation in the atomic size. We already know what is ionization enthalpy. The energy required to remove an electron from the outermost shell is called ionization enthalpy. And with respect to transition elements, there is a slight and irregular variation of the ionization energies. The ionization energy of the 5D transition series is higher than that of 3D and 4D transition series. And this is due to lanthanoid contraction. We already had discussed what is lanthanoid contraction. The steady decline in the atomic and ionic radius from lanthanum to lutetium. This is called lanthanoid contraction, and the imperfect shielding of 4f electrons is responsible for lanthanoid contraction. So when the atomic and ionic radius contracts, we know the outermost electron will be very close to the nucleus, and removal of such an electron will be difficult because the nucleus will be exerting more attractive power towards the outermost electron. So due to this lanthanoid contraction, there is slight and irregular variation in the ionization energies. The next topic is oxidation state. The transition metals show variable oxidation state due to the tendency of N-1d as well as Ns electron to take part in bond formation. So we already had discussed the electronic configuration of transition elements. It will be having incompletely filled d orbital, that means d1 to d9. And when these electrons are taking part in bond formation, this will result in variable oxidation state. So with respect to oxidation state, the transition elements will be exerting variable oxidation state. This is because the N-1d as well as the Nx electrons will be taking part in bond formation, and this will result in difference in oxidation state. The next property is magnetic properties. Most of the transition metals are paramagnetic in nature due to the presence of unpaired electron. For example, scandium, the outermost electronic configuration is 4s2 3d1. That means there is one unpaired electron. In titanium, the electronic configuration is 4s2 3d2. That means there are two unpaired electrons in the d orbital. With respect to Hund's rule, in the case of vanadium, the outermost electronic configuration is 4s2 3d3. That means three unpaired electrons are there in the 3d orbital. So magnetic properties, how do we calculate the magnetic properties? The equation to find the magnetic moment is square root of n into n plus 2, where n is the number of unpaired electrons. So in the case of scandium, the magnetic moment would be square root of 1 into 1 plus 2. Titanium, the magnetic moment is square root of 2 into 2 plus 2. And in case of vanadium, the magnetic moment is square root of 3 into 3 plus 2. So most of the transition elements are paramagnetic nature, and this is due to the presence of unpaired electron. The paramagnetic property increases from scandium to chromium and then decreases because the number of unpaired electron decreases. So that is about magnetic properties. The next is catalytic properties. Most of the transition metals are used as catalysts because of the first reason is presence of incomplete d orbitals, second one is large surface area, and third one is variable oxidation state. We know what is a catalyst. A substance that does not participate in a chemical reaction but speeds up a chemical reaction. For example, many of the D block elements, for example, iron, it is used in the Haber process. Vanadium is used in the contact process manufacture of sulfuric acid. So the reason for these elements exhibiting catalytic properties is there are three reasons for that. First one is the presence of incomplete d orbitals. Second one is large surface area, and the third one is variable oxidation state. So all these are responsible for new bond formation and that result in catalytic properties. The next property is formation of colored compounds. Transition or D block elements result in formation of colored compounds. They form colored ions due to the presence of incomplete filled d orbitals and unpaired electrons. They can undergo DD transition by absorbing the color from the visible region and radiating complementary colors. So all this we have discussed in the coordination compounds chapter. We know the transition elements are having incomplete d orbital, that means d1 to d9, and we have studied the octahedral and tetrahedral splitting. The d5 d orbitals are split into 2 EZ and T2Z, and when light falls on this, the electrons get excited from EZ to T2Z, and later they go back to the same state. And during this, the energy will be absorbed from the visible region, and the compounds will be exhibiting the complementary color. So all that we had discussed in the coordination chemistry chapter. And the reason for exhibiting this colored compound is DD transition, the transaction between EZ and T2Z. So this DD transition is responsible for imparting color. Our last topic is alloy formation. They form alloy due to similar ionic size. Metals can replace each other in the crystal lattice, example, brass. So far, we have discussed all the important concepts of D and F block elements. So now we will be discussing all the important previous year questions from this chapter, D and F block elements. The first question is define the term transition element. The answer is transition element is defined as the one which has got incompletely filled d orbitals in its ground state or in any one of its oxidant state. So we had discussed earlier, for an element to become a transition element, it should have either D1 to D9 electronic configuration. That is, D10 that is completely filled d orbital is not a transition element. It should have incompletely filled d orbital. That means it should be in the range of D1 to D9 in its ground state or in any one of its oxidant state. The second question is give the general electronic configuration of d block elements. And the answer is the rare gas configuration plus n minus 1 d 1 to 10 ns 1 to 2. The third question is why scandium with atomic number 21 is a transition element but zinc is not? The answer is simply scandium has got incompletely filled d orbitals. On the other hand, zinc has got completely filled d orbital. So to memorize the electronic configuration of the atomic number, we have to study a specific order that is given the table. See, the order is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. This order should be memorized and the corresponding atomic number that is from 21 to 30. And the electronic configuration also should be like by heart so that it becomes easy for your exam point of view. So there is a regular pattern in the electronic configuration and the atomic number. Scandium with atomic number 21. First we will discuss the D electronic configuration. That's 3D1 for scandium. Titanium 3D2. Vanadium is 3D3. Chromium is 35. Manganese is again 35. Iron is 36. Cobalt is 37. Nickel is 38. Copper is 3D10. And zinc is 3D10. So there is a specific order from 1 to 10, but in between 3D4 and 3D9 is not there. So that is the only thing to memorize. And about the 4s series, all the elements from scandium to zinc are exhibiting 4s2 except chromium and copper. So you have to memorize this particular name of the element, its atomic number and electronic configuration. Then you will be able to explain the properties with respect to this chapter and even the magnetic properties. So our question was, scandium is a transition element but zinc is not. So if you observe the electronic configuration, you can see scandium, the electronic configuration is 4s2 3d1. That means in the d orbital only one electron is present. That means it has got incompletely filled d orbital and thereby scandium is regarded as a transition element. But in the case of zinc, you can see the electronic configuration is argon 3d10 4s2. That means 3d10. The d orbital is completely filled. And in order for an element to be part of the transition element, the criteria is it should have incompletely filled d orbital. Zinc is having 3d10 electronic configuration and thereby zinc is not regarded as a transition element. Next, the third question is, also the fourth question, write the electronic configuration, calculate the magnetic moment and predict the magnetic properties of the 3D elements. So this particular table is here. And we can see in the case of scandium, it is 3d1 4s2. That means in D there is one electron and there is only one unpaired electron, and the equation to find the magnetic moment is square root of n into n plus 2. So applying the value of n as 1, square root of 1 into 1 plus 2, and you will get the answer as 1.73. And since there is one unpaired electron, it is paramagnetic. Second, the case of titanium, the electronic configuration is 4s2 3d2. That means two unpaired electrons are present in the d orbital. And the equation to find magnetic moment would be square root of 2 into 2 plus 2, and the answer is 2.83. And since unpaired electrons are present, it is paramagnetic nature. So the filling of the 3d orbitals will be done in accordance with the Hund's rule. It says that the pairing of the electrons in the orbitals will take place only after each orbital receiving one electron each. For example, in the case of cobalt, you can see it is 3d7 4s2. So one electron each will be given for each of the 5 orbital, and again the 2 excess electrons that will be paired. So in the case of cobalt, the number of unpaired electrons is only 3, and thereby the magnetic moment is square root of 3 into 3 plus 2. So this is how you find the magnetic moment of the elements of D block. Next, the question number 5. Write the electronic configuration and calculate the magnetic moment and magnetic properties of some of the 3D element ions. So in this question, we are asked to find the magnetic properties and magnetic moment of ions. So we'll be considering scandium 3 plus, chromium 3 plus, manganese 2 plus, etc. The electronic configuration of scandium 3 plus is 3d0 4s0. The normal scandium atom, the electronic configuration is 4s2 3d1. Scandium 3 plus means 3 electrons are lost. So thereby the new electronic configuration is 3d0 4s0. And here there are no unpaired electrons, and thereby the magnetic moment would be 0, square root of 0 into 0 plus 2, that is 0. Since no unpaired electrons are there, the magnetic property is diamagnetic. In the case of chromium 3 plus, the new electronic configuration is, outermost new electronic configuration is 3d3 4s0. That means there are 3 unpaired electrons in the d orbital, and thereby the magnetic moment is square root of 3 into 3 plus 2. And since 3 unpaired electrons are there, it is paramagnetic in nature. Similar in the case of Zn2 plus, the new electronic configuration is 3d10 4s0. And with accordance to Hund's rule, there are no unpaired electrons in the d orbital. It is completely filled. And since all the electrons are paired, it is diamagnetic nature, and the number of unpaired electrons is 0, and thereby the magnetic moment is also 0. The sixth question, write the formula to calculate the spin-only magnetic moment. So the question is to find write the equation to find the magnetic moment, that is square root of n into n plus 2, where n is the number of unpaired electrons. Next, question number 7. Name the element of the first row transition series that A has got maximum number of unpaired electrons in its ground state. Second is has 0 spin only magnetic moment in the plus 2 oxygen state, and C is exhibits maximum number of oxygen state. So the first question is, which is the element in the first row transition series that has maximum number of unpaired electrons in the ground state? So we will refer to this table, and you can see that chromium, in the case of chromium, we can see there is how many, count the number of unpaired electrons, we can see that the number of unpaired electrons is 6. Thereby chromium is the element showing maximum number of unpaired electrons in its ground state. The second question is, which element has got 0 spin only magnetic moment in the plus 2 oxygen state? And in the case of zinc, in this particular table you can see, in the case of zinc, the Zn2 plus oxygen state, the electronic configuration is 3d10 4s0, and it is having 0 number of unpaired electrons, and all the electrons are paired, and if you calculate the magnetic moment, it is 0, and thereby zinc is the element that shows 0 magnetic moment in the plus 2 oxygen state. The third question is, where does the element exhibit maximum number of oxygen state? So we can see that in the case of manganese, you can see manganese is the element that is exhibiting more number of unpaired electrons. So more number of unpaired electron means it is able to show maximum number of oxygen state. So question number 7 once again, which is the element that is showing maximum number of unpaired electrons in the ground state? The answer is chromium. Which element has got 0 magnetic moment in the plus 2 oxygen state? That is zinc. And the element which is exhibiting maximum number of oxygen state is manganese. Question number 8. With reference to the first row transition metals, name a metal which shows maximum number of oxygen state. That is manganese. We already discussed this. Question number B is, among Zn2 plus and copper 2 plus, which is colorless? So we know that the property of color is like connected with DD transition. So to show DD transition, there should be unpaired or incompletely filled d orbitals. So in the case of zinc, we discussed that it is already filled, like d orbitals is completely filled, that is 3d10. So the possibility for a DD transition in the case of zinc is nil. But the case of copper, it has got incomplete filled, or it is incomplete, having incomplete filled d orbital, and the chance for exhibiting DD transition is more, and thereby copper will be exhibiting color, which is blue in color. But in the case of zinc, the DD transition is not possible, and thereby zinc Zn 2 plus will be colorless. Question number C, between titanium 2 plus, which contains more number of unpaired electrons. So the question is between titanium 2 plus and vanadium 2 plus, which has got more number of unpaired electrons. So if you compare the electronic configuration, so you have to write the electronic configuration of vanadium and titanium, and then you have to check which has got more number of unpaired electrons. So when you write the electronic configuration and check which has got more number of unpaired electrons, you can see that vanadium 2 plus will be exhibiting more number of unpaired electrons. Question number 9. Calculate the spin-only magnetic moment for Fe2 plus. Question number B is, which element of the 3D series exhibit maximum oxidation state? So first we will go for calculate the magnetic moment of Fe2 plus. So here Fe2 plus, we are seen that the number of unpaired electrons is 4 and the magnetic moment would be square root of 4 into 4 plus 2. The answer is 4.9. And since it has got 4 unpaired electrons, it is paramagnetic in nature. And question number 9b is, which element of the 3D series exhibit maximum oxidation state? And we already discussed the answer. Manganese is the element that is exhibiting maximum number of oxidation state. Question number 10. Between copper 2 plus and copper plus, which is more stable? So you write the electronic configuration, and based on that you can see that copper 2 plus is more stable. Question number 11. Transition metals are very hard and have got high melting point and boiling point. Give reason. So we had already discussed this question. Like transition metals has got incompletely filled d orbitals. That means so many free electrons are there, and these free electrons are responsible for the metallic character. And due to this metallic character, it has got high melting point and high boiling point. Question number 12. D block elements show variable oxidation state. So this is the same reason. Like transition metal has got incompletely filled d orbitals, and the electrons of the d orbital will be taking part in the bond formation. And when these electrons are involved in the bond formation, this will result in variable oxidation state. Question number 13. Name the transition element which does not exhibit variable oxidation state. The answer is scandium. Scandium does not exhibit variable oxidation state. It will exhibit only scandium 3 plus oxidation state. Question number 14 is, scandium 3 plus ions are colorless while vanadium 3 plus ions are colored. Give reason. So regarding color of a compound, we already studied in the coordination compound chapter. Like the phenomenon behind imparting color is DD transition. That means the 5 d orbitals are again split into 2, EZ and T2Z, and when sunlight energy falls on this, there will be transaction between EZ and T2Z, and the complementary color will be exhibited. So all that we have already discussed. The phenomenon behind the exhibiting color is DD transition. So for exhibiting DD transition, the criteria is that the particular ion should be having unpaired electron. Scandium 3 plus, the normal electronic configuration of scandium is 4s2 3d1. But in the case of scandium 3 plus, that means it is the resultant of losing 3 electrons. So scandium 3 plus means the electronic configuration is 4s0 3d0. That means there are no unpaired electrons. So since there are no unpaired electrons, DD transition is not possible and thereby it is colorless. But in the case of vanadium 3 plus, if you write the electronic configuration, you can see that there are 2 unpaired electrons. And if there are 2 unpaired electrons, a DD transition is possible from EZ to T2Z and vice versa. And thereby DD transition is possible, and thereby vanadium 3 plus ions are colored. 15th is a similar question. Why scandium 3 plus salts are colorless while chromium 3 plus colored salts are colored? It's the same reason. Scandium 3 plus ions, they does not have unpaired electron, that is why they are colorless. On the other hand, chromium 3 plus, you have to write the electronic configuration, and you can see that there are 3 unpaired electrons. If 3 unpaired electrons are there, the transfer of electron from EZ to T2Z and vice versa is possible, and thereby DD transition is being exhibited, and thereby it is colored. Question number 16 is also the same. Why titanium 4 plus is colorless while chromium 3 plus salts are colored? So even without writing the electronic configuration, like it's a common answer. If it is colorless, that means that it is not having any unpaired electron. Thereby it cannot exhibit DD transition, and thus it is colorless. But if a compound is colored or an ion is colored, That is because it will be having unpaired electron and DD transition is possible and thereby it is colored. So the answer is very clear. Scandium 3 plus ion does not have any unpaired electron and hence DD transition does not take place. But on the other hand, chromium 3 plus ions have got 3 unpaired electrons and hence DD transition take place. Therefore, chromium 3 plus ions are colored. If it is a 2-mark question, you have to write the electronic configuration of scandium 3 plus and chromium 3 plus. And you have to pinpoint that scandium is not having any unpaired electron. On the other hand, chromium is having unpaired electron and thereby DD transition is possible and thereby chromium 3 plus is colored. Question number 18. Give any two reasons for the formation of large number of complex compounds by transition metals. Complex compounds means the same as coordination compounds. So we already had discussed the coordination compounds in the 9th chapter. And the reasons for transition metals to be part of the coordination compounds is it has got 3 reasons. First one is small size of the metal ions. Second one is high ionic charges. And third one is availability of empty d orbitals. So high ionic charges, while we write the structure of the coordination compound, we already studied, like the charge of the central metal is exhibiting many properties regarding the coordination compound. So to form a coordination compound, it requires high ionic charges. And the next criteria is availability of d orbital. We know for the ligands to make bond with the central metal, like availability of d orbitals is a need. So these 3 are the factors responsible for formation of large number of complexes. The first one is small size of the metal ion, second is high ionic charge of the metal ion, and third one is availability of empty d orbital for bond formation with the ligands. And another question, what is the element that is exhibiting the highest oxidation states? The answer is manganese. Manganese is exhibiting highest number of oxidation state. That is, manganese is exhibiting oxidation state ranging from +2 to +7. So the question is, which is the element that is exhibiting maximum number of oxidation state? And the answer is manganese. It is exhibiting oxidation state ranging from +2 to +7. The highest oxidation state is exhibited by manganese, and that is +7. And the most common oxidation state being exhibited by the elements is +2. Okay. So that's a 1-mark question. And question number 19. Cu2 plus ions are colored and the Zn2 plus ions are colorless. It's the same concept we discussed earlier. Zn2 plus are colorless because Zn2 plus are not having any unpaired electron, and that is why it is colorless. On the other hand, Cu2 plus ions, if you write the electronic configuration, you can say that there is one unpaired electron, and this can undergo DD transition, and thereby it is colored. Question number 20. Transition elements show catalytic property. Give 2 reasons. So this also we already had discussed. The answer is transition metals and their compounds are known to exhibit catalytic property. This is because of the following reason. First one is they are able to adopt multiple oxidation state. That means due to the incompatible d orbital, it is able to adopt different oxidation state and thereby link with different elements. So first one is that. Second one is we are able to form intermediate complexes. The third one is lowers the activation energy for the reaction. So lowering the activation energy means it is more easy for the reaction to occur. So these are the 3 reasons. Question number 21. What are interstitial compounds? Interstitial compounds are those which are formed by transitional elements when small atoms like hydrogen, carbon, nitrogen are trapped inside the crystal lattice of the metals. So about crystal lattice, we already studied in the first chapter, that is the solid state, and we already know what is interstitial space and the space occupied by the atoms. Interstitial space is the space that is available in the void space in between that. So interstitial compounds are those which are formed by transition elements when small atoms like carbon, nitrogen, etc. are trapped in the lattice of metal, that is the interstitial space. Example is vanadium H0.5. Question number 33. What is Lanthanoid contraction? Write the general oxidation state of actinoids. Actinoids and actinoid contraction has been deleted as per the new syllabus. Similarly, the preparation properties of potassium permanganate, potassium dichromate all has been deleted as per the new updated syllabus. So here what is Lanthanoid contraction? The steady decrease in the size of lanthanoids with the increase in atomic number is called Lanthanoid contraction, and it is due to the imperfect shielding of 4 of electrons. So all we have discussed in the introductory part, we know that Compared to other orbitals, the 4f orbitals are having less shielding effect, and due to this, the nucleus is able to exert more nuclear inward pull towards the outer electrons. Thereby, the outer electrons will be held more strong towards the nucleus, and thereby it will result in contraction. So the Lanthanoid contraction is due to the imperfect shielding of the 4f electrons. And the general oxygen state of actinoids and lanthanoids is +3. So that is a 1 mark question, which is the general oxygen state of lanthanoids and actinoids. So they will be exhibiting the general oxygen state of +3. 34th question is give two consequences of lanthanoid contraction. That means what are the after effects of lanthanoid contraction? So we already studied what is lanthanoid contraction and what is the cause of lanthanoid contraction. Now we are discussing the consequence of lanthanoid contraction. There are two consequences. The first one is radius of the members of the third transition series are very much similar to that of the corresponding second series. The second consequence is very difficult to separate lanthanoids of the second series elements from third series elements in the pure state during extraction. So the two consequences given here. The first one is radius of the third series and second series are almost similar. So we can explain this with the help of the periodic table. So we know that the transition elements are divided into 4 series. The first series is scandium to zinc, second is yttrium to cadmium, third is the series in which the lanthanides are present, and the fourth actinides are present. So as per the first consequence, it is given that the atomic radius of the second and the third series are almost the same. It is because of lanthanoid contraction. See, lanthanoids are present in the space between 58 to 71, and we know that due to lanthanoid contraction, there is an additional decline in the atomic and ionic radius. Thereby, hafnium, which is the post-actinoid element, will be exhibiting almost same size that of the second series element, that of zirconium. So, as a normal trend, as we go down the group, the atomic and ionic radius has to increase because increase in more number of shells. That is a normal trend. Top to bottom of the periodic table, size of the atom increases. But when you compare the second and third series, we can see that in the third series there is lanthanoid contraction. That is, there is a steady decrease in the size of the elements belonging to the lanthanoids. So thereby, if you compare second and third series, due to this lanthanoid contraction, the elements belonging to second series and third series will be having almost similar size. For example, the question will be like this: zirconium and hafnium. Zirconium with atomic number 40 and hafnium with atomic number 72, they are having identical radius. What is the reason? The reason is simply lanthanoid contraction. Due to lanthanoid contraction, normally zirconium should have a small size compared to hafnium. But due to lanthanoid contraction, hafnium is a post-lanthanide compound. So due to this lanthanide contraction, hafnium will be having a comparatively less size. So normally hafnium's size has to be increased, but due to this lanthanide contraction, the size of the third series elements will be almost similar to that of the second series elements. So that is the first consequences. The second consequence is difficulty in separation of the second series elements and third series elements. So some of the separation techniques are based on the size of the atoms, and due to the lanthanide contraction, the second series and third series elements are having almost identical size, and due to this, their separation becomes difficult. So these are the two consequences. So this is a definite 2-mark question. What is lanthanoid contraction, and write two consequences of lanthanoid contraction. So lanthanoid contraction is a steady decrease in the size of the lanthanoids as with the increase in atomic number, and the cause of lanthanoid contraction is imperfect shielding of the 4f electrons. And two consequences is that the second series elements and third series transition series elements will be having almost identical size. Second consequence is that owing to the same size, the separation of these elements becomes difficult. Question number 35. What happens when lanthanides are heated in oxygen, nitrogen, halogen, and carbon? When the lanthanides are heated with oxygen, an example is given. When lanthanum is heated with oxygen, it forms lanthanum oxide. When with nitrogen, it forms lanthanoid nitride. With a halogen, it forms lanthanoid halide, and with carbonate form, lanthanoid carbide, and the corresponding equations are also given here. Question number 36. How lanthanoid react with water and dilute acids? Answer is given there. With water, lanthanoid give hydroxides with the liberation of hydrogen, and the equation is given here. With dilute acid, they liberate hydrogen. So lanthanoid plus dilute gas gives hydrogen gas. So this is the difference in reaction between water and dilute acids. Question number 37. What is mixed metal? Gave one of the use. So mixed metal is an alloy of lanthanoids with iron. That means alloy is a combination of two different metals. So mixed metal is an alloy of lanthanoid with iron. So iron is definitely a part of that alloy, and the lanthanoids will change. So mixed metal is an alloy of lanthanoid with iron. An example is given here. Lanthanoid is present 95% and iron is present as 5%. This particular mixed metal is used in the manufacture of bullets. Question number 41. Zirconium and hafnium has got identical atomic radius, give reason. So already we discussed zirconium is part of the second series and hafnium is part of the third series, and due to Lanthanoid contraction they have got identical atomic radius. So the answer is simply Lanthanoid contraction. So due to this, zirconium maintains an equivalent size to that of hafnium. Question number 43. Give reason why lanthanoids are less reactive than actinoids. So actinoids has been deleted, but still we will discuss the answer. 4 of electrons are firmly held attracted to the nucleus in lanthanoids. See, in lanthanoids, it is the 4 of electron that is taking part, and in actinoids, it is the 5 of electron that is taking part. So, when comparing 4f and 5f, it is clear that the 4f electrons are held more close to the nucleus. So, when we are going for a comparison, the 4f electrons being firmly attracted to the nucleus, it is not easily available for bond formation because they are tightly held towards the nucleus. But 5f in actinoids, it is the 5f that is taking into action. The 5f is little more far away from the 4f. So the nuclear force exerted by the nucleus will be not that much received by the 5f electrons. And that is why 5f will be more reactive. The answer is the 4f electrons are firmly attracted to the nucleus charge. Hence 4f electrons are not easily available for bonding compared to 5f electrons of the actinoids. Question number 44. Out of the following elements, identify the element which does not exhibit variable oxygen state. Chromium, cobalt and zinc. So if you write the electronic configuration, you have seen that the electronic configuration of zinc is 3d10 4s2. That means the unpaired electrons are not there, and thereby it is 3d10 in zinc. So thereby it is not possible to exhibit variable oxygen state due to completely filled d orbital. So the answer is zinc. But in the case of chromium and cobalt, it is incompletely filled d orbital and it can show variable oxygen state because those electrons can take part in bond formation, and that will result in different oxygen states like +1, +2, +3, etc. Question number 45. Give reason. Most of the transition metals have high melting point and boiling point. Question number 2 is second ionization enthalpy of copper is exceptionally high. The third one is atomic size of the 4D and 5D series elements are almost the same. Okay. So the first question is most of the transition metals have got high melting point and boiling point. Because we know that in the transition elements there are more number of unpaired electrons, and this unpaired electron or the free electrons are responsible for the metallic character, and due to this metallic character they are exhibiting high boiling point and melting point. The second question is second ionization enthalpy of copper is exceptionally high. The answer is copper plus ion has got completely filled orbitals, and more energy is needed to remove the second electron from the stable electronic configuration. So if you write the electronic configuration, you can see that Cu plus will be having completely filled, that is 3d10 electronic configuration. So you compare Cu2 plus and Cu. Cu2 plus is the first ionization enthalpy. For the Cu2 plus, the electronic configuration is 3d10 4s1. It is not stable because 4s1 is not completely filled. But if you go for Cu plus electronic configuration, the electronic configuration is 3d10 4s0. That means the 3d orbital is completely filled, and thereby it is highly stable, and removal of an electron from the completely stable electronic configuration is difficult. So that is why the second ionization enthalpy of copper is exceptionally high. The third question, atomic size of the 4D and 5D series are almost the same. So we already had discussed 4D series belong to the second and 5D belong to the third series, and they have got identical radius because of Lanthanoid contraction. It can be also as in the symbol, like in another way, zirconium and hafnium has got the same identical size. What is the reason? It's the same due to Lanthanoid contraction. So if it is a 3-mark question, you have to say it is due to Lanthanoid contraction, and you have to explain what is Lanthanoid contraction. Question number 48, among Fe2 plus and Fe3 plus, which is most stable, give reason. So if you see such a question, the first thing you have to do is write the electronic configuration of Fe2 plus and Fe3 plus. So Fe3 plus is most stable. It is because Fe3 plus has got stable half-filled configuration. So if you write the configuration of Fe3 plus, you can see that it is 3d5. So in terms of d orbital, the stable electronic configurations are d10 and d5, full-filled and half-filled. So full-filled and half-filled configurations are very stable. So when you see such a question, you have to write the electronic configuration corresponding Fe2 plus and Fe3 plus. And for Fe3 plus, you can see that the electronic configuration is 3d5, and for Fe2 plus, it is 3d6. So 3d5 is half-filled. That is why it is having more stability. Question number 49. Manganese exhibit higher oxygen state of +7 among 3D elements. Give a reason for that. The second one is Cu2 plus is paramagnetic and Cu plus is diamagnetic. The answer is due to the participation of all electrons of 3D and 4s orbital in bonding. In manganese, you can see that like all the electrons in 4s and 3D are involved in bond formation. So that is the reason for it exhibiting like oxygen state ranging from +2 to +7. We already discussed manganese is the element that is capable of exhibiting many different oxygen states, that is +2 to +7. The maximum oxygen state exhibited by manganese is +7. This is because there are unpaired electrons present in 3D as well as 4s orbital, and these electrons can be employed in bond formation in different compounds, and thereby in each and every compound it will be exhibiting a different oxygen state. So that is the reason, due to the participation of all electrons of 3D and 4s orbitals in bonding. The second question is Cu2 plus is paramagnetic while Cu plus is diamagnetic. So we already discussed in the coordination compound chapter, the paramagnetic behavior is the resultant of unpaired electron, and diamagnetic character is the resultant of paired electron. Cu2 plus is paramagnetic and Cu plus is diamagnetic. So whenever you see such a question, you have to write the electronic configuration, and you can see that in Cu2 plus there is one unpaired electron, and that is responsible for paramagnetic character. But on the other hand, in Cu plus there are no unpaired electron, and that is why it is diamagnetic. Question number 50. Give reason. Transition metals are generally exhibiting colored compounds. So we had already discussed this. The answer is DD transition. When a visible light falls on a metal ion, the unpaired electron of the d subshell jump from lower energy d orbital to higher energy d orbital by absorbing the light of a particular wavelength. Therefore, the unabsorbed light is transmitted as the complementary color. So we already discussed the d orbitals are split into two, EZ and T2Z. So when the light falls, there will be a transition from EZ to T2Z, and the complementary color which is not absorbed is exhibited, and that is the reason. So the reason for colored compound is DD transition. Thank you.